Hello everyone. There are two more questions that are to be discussed and that are the expected ones. So let's have a look over them. There is an example one for you, that is discuss the behavior of the power series summation n going from 2 to infinity z the power n over n log of n square on the circle of convergence. So whenever there is a question for the circle of convergence, we have to get the value for the mod z, to use that value and to check what is the radius of convergence for that. So let's solve this. If you have your power series as n going from 2 to infinity, and it is given that n should start from 2, this is a n z the power n. This is equal to, it is given that z the power n over n log of n whole square. So if you look, we have an as equal to 1 over n log of n whole square. So if an is equal to this, then what is an plus 1? This is 1 over n plus 1 log of n plus 1 whole square. To find the radius of convergence, I am using the formula limit n tends to infinity mod of an over an plus 1, which is further equal to limit n tends to infinity. This will be your n plus 1 log of n plus 1. If you put the values for an and an plus 1, you will get this log of n whole square. Separating this n plus 1 over n, this will be equal to limit n tends to infinity, taking the limits n tends to infinity for log of n plus 1 whole square over log of n whole square. This limit is 1. Now if you put the limit n over the numerator, you will get infinity, and over the denominator also infinity. So this is infinity of the infinity form. So I'm using the L'Hopital's rule over here, and you take the derivative for the denominator as 2 log of n plus 1 into 1 over n plus 1, and the derivative of denominator 2 log of n into n. Limit n tends to infinity. 2 cancel. So again, separating this limit n over n plus 1 and for limit on this ratio. So I will be getting limit n tends to infinity. This is n over n plus 1. Limit n tends to infinity log of n plus 1 over log of n. We again see that this limit is again 1, and if we check, the numerator again goes to infinity and denominator is also infinity. So this is infinity over infinity form. So I again using the L'Hopital's rule, that is limit n tends to infinity. This is 1 over n plus 1, and this is 1 by n. So this is 1 into, this limit is also 1. So finally I am getting the radius of convergence to be equal to 1. And mod z is equal to 1 is the circle of convergence. As radius is 1, so mod z is 1. So this is your circle of convergence. So for every point z on the circle of convergence, we have our power series, that is, let's check the power series is convergent or not. So for every point z on the circle of convergence. What is your circle of convergence looks like? This is origin, this is 1, as the radius is 1, so circle of convergence is mod z is equal to 1. This is your x-axis, this is your y-axis. Okay, so for every point, that is all the points on the circle of convergence, for that I am checking my power series, that is 2 to infinity mod of z the power n over n log of n square. What is this mod equal to? 2 to infinity, should I write it like this? Mod z the power n over n log of n square. Now on the circle of convergence, this mod z is equal to 1. So this is n going from 2 to infinity. This is 1 over n log of n square. Okay, let's check whether this series is convergent or not. So far we have not used yet the Cauchy's condensation test. Let's use the test now. What is the Cauchy's condensation test says? Do you remember this test? Alright. This test says that if an is greater than equal to an plus 1, further greater than 0, for n 0, 1, 2, 3, then the summation n going from 0 to infinity an, this is convergent if and only if summation n going from 0 to infinity to the power n, a to the power n is convergent. Okay, so in this solution we have our an as, let's take this as your an. Okay, so since if you look at this term, that is 1 over n log n square, this can I write this is greater than equal to n plus 1, since I must have that an should be greater than equal to an plus 1. So let's change n to n plus 1 and see whether it is greater or not. Yes, it is greater than equal to this. Why? Because the denominator is more than n. This n plus 1 is more than n. So denominator is more here. So this fraction is lesser. So this is greater than equal to 0. Why greater than 0? Because this is also positive and this is also positive, since it's a square. So whole thing is positive. So this is greater than equal to 0 for n starts from 2. Okay. Now this is convergent. Now this thing is convergent if and only if. So I write by Cauchy condensation test, summation 2 to infinity n log of n square is convergent if and only if summation n going from 2 to infinity 2 raised to the power n over, instead of n I should write 2 raised to the power n log of 2 raised to the power n whole square is convergent. So let's check this whether it is convergent or not. If this is convergent, then this thing is this series is convergent. If this series is convergent, then the given series is convergent on the circle of the convergence for all the points. So let's check this. Summation n going from 2 to infinity. You cancel this 2 by n. I'm okay. On the next step, I will write. This is summation n going from 2 to infinity. Using the logarithmic rule, the power goes to the left side, n log of 2 square. Take this number outside. Limit is on n, so this is 1 over n square. Now by p-test, as this power of n is greater than 1, so this is convergent by p-test. So this series is convergent. So this is convergent, so hence summation n 2 to infinity 1 over n log of n square is convergent by Cauchy condensation test, and hence the given series converges. Hence the given series is convergent for every point z on the circle of convergence. Fine. Okay, so here the solution ends up. Let's have our next example, which is also very important and expected one. Investigate the behavior of summation z the power n over n the power series starts from 1 to infinity on the circle of convergence. Alright, let's start. Again, let's take our power series, that is a n z the power n is equal to what is given. This is z the power n over n. From here, a n is equal to 1 by n. Okay, a n is 1 by n. I'm not using a n plus 1 now because it is convenient of using the another formula for radius of convergence, that is mod of a n the power 1 by n, which is equal to limit n to infinity. What is a n? This is 1 by n power 1 by n. Okay, if you put the limit, this is n the power 0, 1 by infinity is 0, so this is 1 finally. The limit comes out to be 1. So therefore r is equal to 1 is the radius of convergence, and mod z is equal to 1 is the circle of convergence. Okay, so let's look at our circle of convergence. You are having the circle of convergence as radius is 1, so this is mod z is equal to 1. Now you are having all the points z over here. Okay, this point will be 1. This is z is equal to 1 and this is minus 1. So if you look your given power series, that is z the power n by n. Oh, what a good nice thing is there. If suppose z is 1, that is if I take this point 1, then what is my series behavior is? This is summation 1 by n. Oh, this is a divergent series. So at z is equal to 1, the given power series is divergent. So at other points, is it convergent or divergent? Let's check. So from the diagram, I get the point that is at this is your first thing, z is equal to 1, where? On the circle of convergence. On the circle of convergence, the given series become summation 1 over n, which is divergent. तो ये तो देखते ही पता चल गया, डायग्राम को देखते ही पता चल गया कि इस पॉइंट पे तो सीरीज डाइवर्जेंट है. ठीक है, देखते हैं बाकी पॉइंट्स पे क्या होता है. सो लेट्स चेक फॉर अदर पॉइंट्स. सो फॉर z not equal to 1, what happens? Let, I'm using the Dirichlet's test over here. I'm taking my u and z to be equal to z the power n from the given power series and choosing vn is equal to 1 by n. Why I have chosen the Dirichlet's test? Because if you look at over here, your vn is 1 by n if, then this is monotonically decreasing sequence and it also converges to 0 as n going to infinity. So the other thing is that is u and z, this should have bounded partials. If this both thing happens, then by Dirichlet's test, the given series is convergent. So from the given series, I have taken u and z to be z the power n and vn to be 1 by n. Clearly, this vn, that is 1 by n, this sequence is monotonically decreasing and converging to 0 as n goes to infinity. So now let's check the bounded partials for u and z. So I'm taking the partials that starts from k equal to 1 to n. Instead of un, you should write ukz, which is equal to summation n going from 1 to, sorry, k going from 1 to n. I'm very sorry. What is ukz? It is z the power k. If you open this, you will see that this is your GP series. Okay, sorry, z the power n. So what is the sum for the GP series? That is a into 1 minus r the power n. R is your common ratio, that is also z, over 1 minus r. This full mod. Taking z inside, this is z minus z the power n plus 1 over 1 minus z mod. Now on the circle, okay, mod of a minus b is less than equal to mod a plus mod b. अब जब मुझे इनइक्वालिटी का साइन लेस देन इक्वल टू ऐसे मिल गया है, सो मेरे बाउंडेड पार्शियल्स आ रहे हैं. So on the circle of convergence, this mod z is 1. Mod z is equal to 1. So this is 1. This is also 1. The sum makes 2. 1 minus z. So u and z has bounded partials. So thus summation n going from 1 to infinity, u and z has bounded partials sums. So therefore by Dirichlet's test, the given series is convergent or converges on the circle of convergence except what point except z is equal to 1, because z equal to 1 पे सीरीज आपकी डाइवर्जेंट थी. सो उस पॉइंट को छोड़कर बाकी सारे पॉइंट्स पर वो सीरीज आपकी कन्वर्जेंट है. लेट्स सी. Skipping this point, for this point, the series is divergent, and for the rest of all the points, the series is convergent. Okay, so the given series is convergent on the circle of convergence except z is equal to 1. Okay, so for every value of z. Wait, let's write like this. The series is convergent on the circle of on all the points on the circle of convergence. On all the points except z equal to 1 on the circle of convergence. So here the power series ends up. So for my next content, that will be based on Green's theorem, singularities, and residue theorem, and much more. Do subscribe my channel, and thank you for watching all the series, for all the content that is on the power series. So thank you.